Welcome back to part 2 of our training series, Introduction to OBD2 and Electronic Vehicle Diagnostics. If you've made it this far, you already know how critical vehicle electronics and communication networks are. Now it's time to put that knowledge into action. We'll take a closer look at the core functions that almost all diagnostic scanners share, including reading and clearing diagnostic trouble codes and viewing live data streams.
Introduction to OBD2 and Electronic Vehicle Diagnostics.
When a malfunction occurs, a diagnostic trouble code, DTC, will be set on the ECU to record the problem. These DTCs can be read using a diagnostic scan tool. A diagnostic scan tool is a computer used to communicate with modern vehicle electronic control units. There are a few different types of diagnostic scanners: the PC-based interface, the handheld all-in-one scanner, and the basic OBD2 code reader. The pros and cons of different scanner types. In terms of durability, the handheld is most rugged, designed with covers and protection. The PC-based, the interface is usually rugged, but the laptop PCs are quite fragile. The code reader can be rugged, but some are fairly delicate. In terms of mobility, the handheld is usually very mobile. PC-based, more cumbersome due to laptop and cables that must be carried around with it. The code reader, usually very small and mobile. In terms of software, the handheld, it has a fixed operating system and is usually very reliable. Update by connecting to a PC or by removable media. It has limited data storage. The PC-based stuff, specific software for the interface may have specific operating system and PC hardware requirements. For example, Mercedes-Benz Century can only be run on an IBM T30 computer. A positive, though, is unlimited data storage. The code reader is usually fixed and limited to very specific functions. In general, the handheld is the best universal tool, but is also the most expensive. It has limited screen resolution, but requires limited computer knowledge to operate. The PC-based stuff is usually the best for individual makes, but often have setup issues. They require a good PC knowledge. They have unlimited screen resolution and software application options. The code reader is a cheap solution for quick diagnostics. It has limited functions and is easiest to use. Diagnostics terminology. The diagnostic link connector. It refers to the port or the plug used to connect the diagnostic scanner to the vehicle. It varies on older vehicles, usually found in the engine compartment. In newer vehicles, it is standardized to the OBD2 16-pin found within reach of the driver. DTCs, diagnostic trouble codes, records the indicated faults on a specific electrical circuit. Several names are used interchangeably by different manufacturers to indicate fault codes. Fault codes, fault memory, trouble codes, troubleshooting, and self-diagnostics. Listed are the main functions of a diagnostic scanner. They will be discussed in more detail over the next few slides. To read diagnostic trouble codes. This is the main and most basic diagnostic function. The scanner will retrieve the DTCs stored in a specific control unit. The definition of the code is interpreted by the software. The scanner must also be able to clear or reset DTCs. It must be remembered that fault codes are the results of tests that the ECU runs on specific circuits. In other words, the system must be designed to perform a specific test. Sensor and actuator failures are easiest to detect as the ECU is constantly communicating with them. Unless there is a specific test, wear-type failures are not picked up as trouble codes. So there's no fault code for when a car is losing power or has a flat spot or is losing compression. If a car has a specific wear sensor, like BMW brake pads, then only will you see a fault code. This is an example of a diagnostic trouble code printout. The fault code is 18038. The definition of the fault code is accelerator position sensor, signal too low. There is further information given by signal too low. The G79 figure is a position indicator which will show the position of the sensor on the wiring diagrams or in the workshop manual. Live data. Data parameters to track the sensor and actuator data from the control units. These values indicate the actual measurements at the sensors and can give indications of temperature, flow rate, pressure, etc. After fault codes, live data is the next most useful way of diagnosing a problem. With experience, one can identify what certain values certain sensors should be reading, and use this data to identify malfunctioning sensors. Note that different terms may be used by different manufacturers to indicate the same thing. Data stream, actual values, data monitors. This is an example of live data. It shows the voltage at terminal 30 is 13.6 volts, the voltage status is 10, terminal 15 is on, and the S contact is activated. Actuations are verification tests to confirm the functionality of a particular electrical circuit, sensor, or actuator. This is done by switching on or off circuits using the diagnostic scanner. Once again, several names are used interchangeably to indicate actuations by different car makers. Actuations, functional tests, active tests, final control diagnosis, output tests, and drive links. So in the old days, if a customer told you their car was overheating and you wanted to test the fan, you would have to run wires from the battery to the fan. Using the actuation function, you would simply select fan relay and switch it from the diagnostic scanner. The fuel pump could also be tested in this way. The systems that can be tested vary from vehicle to vehicle. Adaptations. To calibrate the performance parameters of certain control units or components to factory defaults. To adjust parameters such as idle RPM, suspension level, etc. Names are used interchangeably for the same thing by different manufacturers. Control unit adaptations, basic settings, work support, and calibration. The most common example is the throttle body on drive-by-wire VW vehicles. If the throttle body is removed during servicing, the throttle flap may move during the process. When it is replaced, the system may think that the flap is at 0 degrees, when it may actually have moved to 5 degrees. This may result in idling or fueling issues. Throttle body adaptation would recalibrate the system and ensure that the throttle flap is set at 0 and matched to the system. To reset the service indicator for the vehicle, such as oil service or service reminder light. Note that a service reset is a different operation from a fault reset. On most vehicles, a service reset can be done without a diagnostic scanner if the vehicle is within its service schedule or slightly over, by a procedure on the dashboard. A service warning is an information display based on time or distance read from the vehicle dashboard. Thus, the service reset is an instrument cluster function and not an engine function. Component coding. This refers to changing the parameters of a control unit to match a specific vehicle. This usually needs to be done when exchanging or replacing components, for example an automatic transmission. The purpose of coding is to program a control unit so that it knows in what vehicle it's in and with what other controllers it should be communicating with. When a control unit is fitted in a vehicle, it must communicate with other control units. For example, speed data is transferred between the ABS control unit and the transmission. The coding of the control unit tells each control unit with what other control units it should be communicating and what information should be receiving and transmitting. If a unit is not coded correctly, it will report fault codes if it is looking for information from a control unit that is not available. The coding value 13121 gives the control unit the information it needs to function. It defines the control units that the control unit must communicate with. The coding process varies from make to make. It is good practice to record the coding of a control unit before removing it. Thus, it can be easily written to the new control unit once installed. Key coding. Most modern vehicles make use of a transponder key that is linked to the vehicle's ECU. When new keys are cut or an ECU is exchanged, it's necessary to match the key to the ECU. Key coding is a specialist programming function that is available on most professional diagnostic machines. Certain vehicles will require a PIN code to perform the key coding function, which the diagnostic scanner may not be able to give you. The PIN code is usually obtained from the vehicle manufacturer. Programming refers to the correcting or recalibrating of the ECU data due to software changes by software update. Programming is also called flashing. Modifying of the ECU data for more performance or chip tuning is also a form of programming. Chip tuning refers to the process of modifying a vehicle's programming in order to achieve performance or economy gains. It is usually done in conjunction with other mods, like exhaust or intake mods. In the past, chip tuning was performed by physically changing a chip in the ECU of the target vehicle. In the modern vehicle, the chip tuning refers to the three following steps: downloading the information from the vehicle's ECU, modifying the ECU file, then loading the modified ECU file back into the vehicle to achieve the desired performance enhancements. A flashing interface or device must be used to perform the file transfer between the ECU and the storage device. In most cases, the flashing device is not a diagnostic scanner and will not perform diagnostic functions. Examples of flashing devices are the KWP, SPI, and BDM units. This is an example of the hexadecimal code within a control unit that represents the data within it. This is the same hex code with some line numbers added and some converted to ASCII. You can see some data that looks like a VIN number. Here you can see some patterns. These patterns form the ECU maps that determine how the systems perform. Drawn as a 3D graph, this is how it looks. By modifying the shape of the graph, one can change the performance of the systems. Sensor simulation. Sensor simulation is an advanced function available on certain diagnostic machines. It refers to the capability of artificially simulating the functioning of a specific sensor. For example, if a vehicle is showing a fault code, the simulation function will allow you to artificially input the correct sensor output to the ECU. The sensor simulator can allow you to confirm whether a fault code is caused by a sensor failure or a wiring fault. The advantage of this is that if a sensor is not faulty, it saves on unnecessary replacements.
Controller Area Network Diagnostics. CAN electrical systems began to appear in newer vehicles in around 2003. It is a communication standard that allows the various modules and computers in a vehicle to talk to one another via a common data bus circuit in the wiring system. CAN was created in 1984 by the Robert Bosch Corporation. The first production application was in 1992 on several Mercedes-Benz models. Today it is found on most new vehicles. In a CAN bus system, all the control units are connected to each other by a common set of lines. Due to the linear structure of the network, the CAN bus is available to all other modules in the case of a failed or disconnected control unit. This is referred to as a tree structure, with each module occupying a branch. The main bus is referred to as the trunk, with the individual control units occupying the branches. Every module that's attached to the data bus network is capable of sending and receiving signals. Each module or node has its own unique address on the network. This allows the module to receive the inputs and data it needs to function, while ignoring information intended for other modules that share the network. When a module transmits information over the network, the information is coded so all the modules recognize where it came from. Data is sent as a series of digital bits consisting of zeros and ones. If you looked at the data on an oscilloscope, you would see a square wave pattern that changes between a high and low voltage reading. The diagram shows CAN bus signals as they would be seen on an oscilloscope. Two channels are shown, CAN low on one channel and CAN high on the other. The CAN low is normally at a higher voltage, 2.5 volts shown, and goes low, 1.5 volts, when a signal is present. The CAN high is normally at a lower voltage, minus 0.5 volts shown, and goes high, 0.5 volts, when a signal is present. This is referred to as a balanced line transmission. The signals are inverted and at the start and end of the transmission. This results in good noise rejection. 4 CAN words are shown in the display. This diagram shows a CAN base frame. This shows the typical data present in each CAN word. First is a start frame, then an 11-bit identifier code, next a priority code, which allows important messages to go through first, next the actual message data, a cyclic redundancy check, which is a data integrity check. The message will be rejected if it fails the CRC, and finally an end of frame bit.